Have you ever wondered how the universe came into existence? If the universe truly had a beginning, then what was there, if anything, before everything began? Was it absolute nothingness? Or something we still don't have the language or physics to describe? Some even argue that our universe may have emerged, almost forcibly, from a state that looked like pure nothing under the rules of quantum mechanics. And once you take that possibility seriously, the transition from nothing to something stops being a poetic line from mythology and becomes a physical process, something you could, in principle, written into an equation. But that immediately raises a deeper question. When we casually say nothing, does that truly match the physical meaning of nothingness? Humans have circled around this question for thousands of years, just using different languages in each era. In Chinese mythology, the most familiar answer is the story of Pangu splitting heaven and earth. In the beginning, everything was a single chaotic mass, like a giant, undifferentiated cosmic eggs. Pangu awakened inside it, swung his axe. The clear elements rose to form the sky. The heavy ones sank to form the earth, and order emerged. It sounds neat, like the universe had a clean starting point. But take one step back, and new questions surface immediately. What existed before that chaos? Before Pangu could swing an axe, what was there? Is that earlier things just a deeper layer of chaos? Or something that cannot even be called chaos? Mythology cannot describe that layer. It starts the story only from the moment Pangu acts. Later, science took over. It replaced the entire storytelling toolkit. New concepts, new math, new grammar. Through telescopes, spectra, and the cosmic microwave background, we now know the universe has not always been quietly sitting there. According to our best models, more than 10 billion years ago it was extremely hot and dense, and has been expanding and cooling ever since. This picture explains many facts. Why the sky is filled with faintings, uniform microwaves, why the ratio of hydrogen and helium is exactly what it is, and why galaxies form a cosmic web on large scales. From many angles, the Big Bang is a triumph. But once you admit the universe had an early stage, the same old question bubbles up again. Before that, what? Was there another universe before ours? Another phase of physics? Or was there truly a period of absolute nothingness? Cosmologists certainly don't believe in Pangu's axe, so new models emerged. Some propose a cyclic universe. The previous universe collapsed, reached an extreme, then bounced and gave birth to the next one. Others imagine higher dimensional membranes floating in a larger space, and our universe is the result of two giant brains colliding, throwing off a spark of creation. To most people, these ideas already seem wild, but at least they involve something: collisions, cycles, structures. They feel more acceptable than a universe appearing from literal nothing. Yet the most unsettling idea is also the simplest. Maybe our universe didn't inherit anything from a previous one, nor emerged from a higher dimensional structure. Maybe it emerged from physical nothingness itself. If that's true, we must face a deceptively simple but extremely sharp question. In modern physics, what does nothing even mean? Is it an empty vacuum? Or a state without space, without time, without the stage itself? Because if there is no stage, can we even use words like process or emergence? If the universe truly arose from nothing, is that nothing a special physical state? Or have we reached the edge of what science can explain? To chase the real answer, we must return to the physics revolution of the early 20th century, the moment that reshaped the question, what is reality? And dragged the concept of nothingness out of philosophy and into the laboratory. By the late 19th century, people knew matter was made of atoms, and atoms had internal structure. Electrons orbiting a nucleus of protons and neutrons. The earliest intuition imagined atoms like miniature solar systems. But plugging classical electromagnetism into that picture, and disaster strikes. A charged particle in accelerating motion must radiate energy. So electrons should spiral inward and crash into the nucleus. Atoms should collapse. Matters should not exist. Yet the world is stable. So something about atomic rules had to be fundamentally different. Max Planck, trying to fix the mismatch between theory and thermal radiation experiments, made a radical assumption: energy cannot vary continuously. It must be exchanged in discrete chunks quantis. This strange idea opened the path to quantum mechanics. Soon more bizarre facts piled up. Atoms emit light only at specific frequencies. Electrons occupy only specific energy levels, and they transition between them in jumps. Schrödinger described electrons as wave functions, fuzzy probability clouds rather than tiny planets. Heisenberg took a different path. He threw out the orbit picture entirely, kept only what experiments measured, the frequencies and intensities of transitions, and built new rules using matrices. In the end, Schrödinger's waves and Heisenberg's matrices turned out to be the same theory. Heisenberg famously suffered from severe hay fever and escaped to a small North Sea island to recover. There, exhausted and frustrated, he realized he'd been asking the wrong question. Not what path does the electron take, but what does the experiment actually tell us? And from that perspective he reached the unsettling conclusion: on small enough scales, nature refuses to give us both the position and momentum of a particle at the same time. Uncertainty is built into reality, and uncertainty wasn't limited to position and momentum. Energy and time share the same kind of relationship. If you restrict the time window, energy must fluctuate. Push this rule one step further, apply it to the vacuum, and the story transforms. Classical physics imagines the vacuum as a perfect emptiness. No particles, no radiation, no fields, just smooth spacetime. Quantum field theory says this is impossible. Every field, electromagnetic, quark, everything, must fluctuate even in its lowest energy state. Virtual particles constantly appear and vanish. The vacuum is like a pot of soup that looks calm from afar, but up close is always softly bubbling. This is the quantum vacuum, and it destroys the classical notion of pure nothingness. Once spacetime exists, absolute silence is gone forever. This subtle noise changed more than philosophy. It shaped the stars. In history, humans worshipped the sun. Science later asked, what fuels is it? How long can it shine? Kelvin, lacking nuclear physics, calculated that the sun could shine only tens of millions of years, too short for geology or evolution. The problem wasn't his math. Humanity simply hadn't discovered nuclear energy yet. With 20th century revelations, radioactivity, protons, neutrons, and strong nuclear forces, we learned that nuclear fusion powers stars. But even then a puzzle remained. Fusion shouldn't happen easily, because positively charged nuclei repel each other. Classical physics predicts the sun shouldn't ignite at all. Gamow brought quantum mechanics into the heart of the stars. He realized nuclei are wave functions, not hard balls, and quantum tunneling allows a tiny fraction to slip past the energy barrier. Tiny probability, massive scale. The sun ignites, the sun lives. As massive stars collapse, neutrinos, ghost-like particles, flooded outward in unimaginable quantities, triggering supernova explosions and scattering heavy elements into space, seeding future planets and life. Quantum rules are everywhere, in atoms, in stars, and in the first moments of the universe. So naturally the question arises, if atoms and stars obey quantum rules, why not the entire universe? In quantum language, a system's complete state is encoded in its wave function. So could there be a wave function of the universe? If so, the classical Big Bang singularity, that sharp beginning, might just be a limit where quantum effects were ignored. Hawking and Hartle found that near the beginning, time itself becomes fuzzy, blurring into space. The universe may have smoothly emerged from a quantum state, not popped out from a singular point. To explain the universe's uniformity and flatness, physicists proposed inflation, a brief period of exponential expansion. Inflation was initially invented to solve a completely different problem: the absence of magnetic monopoles predicted by high-energy theories. But inflation did much more. It stretched tiny quantum fluctuations to cosmic scales, freezing them into the structure of space. Those fluctuations became tiny density variations, which gravity amplified into galaxies, clusters, and cosmic webs. The cosmic microwave background radiation is a snapshot of those early quantum ripples. The slight temperature differences, only 1 part in 100,000, map the seeds of all future structures. In this sense, the universe we see today is the amplified noise of quantum vacuum fluctuations during inflation. So some physicists asked a nearly joking question: if the quantum vacuum can fluctuate, and if the total energy of the universe might be zero, could the entire universe itself be a vacuum fluctuation? Edward Tryon proposed this idea in the 1970s. People laughed at first, but he was serious. If positive energy, matter and radiation, and negative energy, gravity, balanced to zero, then quantum rules allow a fluctuation of zero total energy to last indefinitely. A universe requiring no energy to exist could persist forever. But then the deeper questions returned, sharper than before. If the universe is a fluctuation, volatility relative to what? What underlying structure allowed that fluctuation? Where did spacetime itself come from? Every time we push the boundary back one step, the question of nothingness reappears. And maybe that is the real message of modern physics. The closer we come to the beginning of the universe, the harder it becomes to even define what nothing means. Maybe nothingness has layers. Maybe the universe didn't start from absolute emptiness, but from the West energy state allowed by quantum rules. Or maybe nothing is simply a word for something we don't understand yet.